The locomotive power reverse gear is one of the most interesting appurtenances on the modern steam engine. This seemingly simple device is deceptively complex in its engineering and execution. The power reverse is used to raise and lower the lifting link on a Walschaerts or Baker type valve gear. The design allows the engineer to operate the timing of a locomotive with a small quadrant rather than manually forcing the lifting link into position with a Johnson bar. Countless engineers were hurt or killed before this type of equipment was available or required. In 1933, the Interstate Commerce Commission made the power reverse a safety device and included it into the Boiler Inspection Act as Rule 157. The rule required that locomotives built after 1933 would have a power reverse, and any engine built before that date weighing more than 150,000 pounds and used in road service would be retrofitted. The weight limit was even less for switchers. There were a few types of power reverse gears common in the railroads of the day, but the most prevalent were the American Locomotive Company's Model G and H. Fast forward 80 years or so to the Virginia and Truckee Railroad's number 29, a 1916 280 Baldwin. This elegant engine has a shop-built power reverse patterned after the Alco Model G. She served a long life in revenue service, but in the winter of 2014, the power reverse gear was in desperate need of a Class 3 back shop. Thomas Gray, the owner of the V&T, removed the valve assembly from the power reverse gear and sent it down to our shops for diagnosis and repair. When it arrived, we disassembled the valve to see if there was anything obviously wrong. The first thing we noted was the crank arm keyway was completely worn and there was 5 to 10 degrees of lost motion on the shaft. There was also a 5/16 Allen head screw used as a pin to hold the crank to the shaft. This was loose and in danger of shearing if the crank's keyway wore any further. The next thing we noticed was the valve assembly was not centered to the keyway on the main shaft. This makes the quadrant position have to be adjusted off of center to bring the engine into a neutral position. The main shaft was 10 thousandths undersized, and the bushing it was riding in was scarred and completely devoid of lubrication. The lubrication point was entirely covered in engine grease and road debris, and in a location that was totally inaccessible. The biggest contributor to the failure of the valve was the design of the rotary valve attachment to the main shaft. The rotary valve was secured to the main shaft with a steel pin driven through both parts. This arrangement would not allow the valve to float against the face of the mating part. Since it couldn't float, as the parts wore, the surfaces were pushed out of alignment with each other and the valve started to leak. The first thing we did was to use bluing and a surface plate on the valve face to find any low spots. There were clearly 2 worn areas that would allow blow-by when the valve was at rest. We ground the face of the valve on a surface grinder until the faces were flat. Then we faced off the rotary valve in the lathe and machined a new connection point for the main shaft. We turned a new main shaft, installed a keyway, and then added 2 studs that would allow the rotary valve to float on the face. The connection point now has more than 1/16 of an inch of motion in all directions. This will ensure the faces of the valves can stay in contact. A new bronze bushing was made and pressed into place. This replaces the original one that was worn and out of round. The new bushing has greaseways machined into it, so the main shaft will always have lubrication. The original spring did not have any way to keep it centered on the valve. In fact, we found it pushed way off center when we opened the case for the first time. So we made a spring holder that rides on a ball bearing at the rear of the case. This allows it to move slightly in any direction. And another holder at the rotor that keeps the spring centered on the back of the valve all the time. A new crank had to be constructed because the original one was way beyond repair. The keyway was broached centered to the valve to eliminate the 10-degree offset the previous crank had, and a pin was made to use as a limiting stop instead of allowing the crank to hit the stop collar as it had in the past. The stop collar itself was heavily modified to allow better access to the bolt that tightens the crank to the main shaft. More than half the material was machined off, and a slot was made for the limiting pin. After all the machining was done, all the parts made one more trip through the sandblaster for cleaning, and then it was time for paint. As always, the paint is really a high solids polyurethane industrial coating. The coating should be good for years of service in a harsh environment. Before final assembly, the valve faces were lapped together to ensure there were no fine scratches or other tool marks that might allow the valve to leak. We made new gaskets to replace the 1/8-inch thick EPDM that was in the valve when we received it, and all new hardware and pipe fittings completed the job. The finished valve assembly was shipped back to the Virginia Truckee Railroad to be returned to service for the 2014 season. So the next time you find yourself in Virginia City, take a look at the side of number 29 and see one of the most interesting and overlooked parts of a steam locomotive.